Okay, so think about this. You've got a puzzle, right? Maybe two numbers, and you know their sum is 10, but their difference is 2. How do you actually find those numbers?
Or maybe you've got money in two different accounts, different interest rates. You know the total you invested and the total interest you got back.
Yeah, how much is where? Solving those kinds of like multi-part problems is exactly what we're getting into today based on your source material.
That's right. Your sources are really focusing on simultaneous linear equations. Essentially, they're pairs of equations, usually with two variables, let's say x and y.
And the goal is?
The goal is finding that one specific pair of values, one x and one y, that makes both of those equations true at the same time.
Gotcha. And the sources give a nice clean example. $2 y on 1 and $3 plus y for 26 months. So we need the x and y that fits both.
Exactly.
Okay, so our mission here is to kind of quickly unpack the different ways your sources suggest for solving these, the algebraic ways, and maybe see where they're most useful.
Absolutely. The sources really lay out three main algebraic techniques. Think of them as, different tools you can pull out.
Okay, first one up is elimination by substitution. What's the basic idea there, according to the sources?
Well, with substitution, the key thing is you rearrange one of the equations. You get one variable, say y, written in terms of the other variable, x. So like from $2.111, it's pretty easy to see that y must be 2 by 1, 1.
Right.
Then the sources show you take that expression, that 2 by 1, 1, 1, and you substitute it into the other equation where you see y.
Ah, okay. So in our example, you'd swap out the y in $3 plus y, $14.4.
You got it.
So it becomes $3 plus 2 by 1 is equal 14th here.
Exactly. And the beauty of that, you see, is suddenly you've only got x left in the equation. It's just one variable.
Much easier to solve then.
Way easier. You find x, then you just plug that value back into your y does 2 by 1 and 1 expression to find y. The source would point out this is like really handy if one equation practically gives you one variable already.
Okay, got it. Replace one with its equivalent. Makes sense. What's the next toolkit item?
That would be the method of elimination by equating coefficients.
Equating coefficients.
Okay, here the strategy is a bit different. You want to fiddle with the equations, maybe multiply one or both by some number.
Why would you do that?
So that the number in front of one variable, the coefficient, becomes the same in both equations. Or maybe the same number but with opposite signs like +3 and -3.
Ah, okay. So you might multiply the whole equation through.
Precisely. Scale them up. And actually, look at our example again. $2 and y 1 and 1, 1, and $3 plus y 14 all in 1. The y coefficients are already -1 and +1.
Oh, right. They're opposites already.
Perfect setup. So the source shows, in this case, you can just add the two equations together, straight up.
$2 plus y equals $1 plus $14.30.
You got it. The jam plus would cancel right out. You're left with $5 equals $15.
Wow, that's fast. Just add them and your vanishes.
It really is. This method can be super quick if you spot coefficients that are already lined up or, almost lined up.
Okay, efficient. And the third method, mention.
That's cross multiplication. Now, this one is a bit more formulaic.
Formulaic.
Yeah, you need to write both equations in a specific standard form first, like $a$x plus b1y plus c1 plus c1. Then the source gives you this kind of pattern, a specific recipe using all the coefficients and constants.
To directly calculate x and y.
Exactly. It spits out the answers for x and y. It's maybe less intuitive. You don't quite see the elimination happening like the other methods. But if you remember the pattern, it works.
Okay, 3 different algebraic approaches. Substitution, equating coefficients, cross multiplication. Now, something I noticed in the sources that was really interesting was that these methods aren't just for equations that look, perfectly linear from the get-go.
That's a really important point.
Yeah.
Yeah, the sources definitely cover how some equations might look nonlinear. Maybe they have terms like eighth by other dollars.
Right, like fractions with the variables in the denominator.
Exactly. But you can often do a little trick, a substitution, to make them look linear.
How does that work?
Well, you could say, let's pretend all the store and fillaballers and two ills to a line. You substitute those new variables, a and b, into your original tricky equations.
Ah, and suddenly you might have linear equations, but with a and b instead.
Precisely. You get a system that looks like, say, $2 plus 3b equals 5 and 5. You solve that system for a and b using substitution or elimination methods we just talked about.
And once you have a and b,
you just remember that a doll was really all the vol and hours and ball is 20 the lie.
Yeah.
So you can easily flip them back to find the original x and y. It's a clever way to extend these techniques.
That is pretty neat. And fundamentally, all of this ties back to solving those real-world type puzzles we started with, right?
Absolutely. The sources give examples about ages or costs or maybe mixing things or distances and speeds.
Yeah.
The key is translating the words, the conditions given in the problem, into two separate linear equations. Each piece of information often gives you one equation.
So you read the problem, pull out the two conditions, rate the two equations.
And then you pick your favorite tool substitution, elimination, and solve the system you've just created.
To find that unique pair of values that fits both conditions of the original problem.
That's the essence of it. Finding that single point, that single solution, that works for everything simultaneously.
Okay, so just to recap briefly, we've seen three main algebraic ways from your sources to tackle these pairs of linear equations. Substitution,
Elimination by equating coefficients,
and that formula-based cross-multiplication. Plus, that neat trick for handling equations that don't look linear at first glance by using a temporary substitution.
Right, turning them into a solvable linear form.
And we saw how all these tools are really aimed at cracking word problems, translating real-world conditions into a system, and finding those specific values that satisfy everything.
It really boils down to finding the unique answer when you have two constraints.
So here's a final thought to maybe chew on, based on what the sources presented. When you look at a pair of equations, how does the way they're written, their actual structure, maybe hint at which method might be fastest?
Yeah.
Like, if you see a variable all by itself with a coefficient of 1, does that scream substitution? Or if the coefficients look like multiples of each other, does that push you towards equating coefficients?
That's a great question to consider.
Yeah, which tool fits which specific equation set up best? Something to perhaps think about next time you're faced with one of these systems.